Part I. Given that y equals tan x plus 2 cos x, find the exact value of dy by dx when x is pi over 4. So let's differentiate this. So we'll get dy by dx. The tan differentiates to be sec squared, and cos we know differentiates to be minus sine. So 2 cos x will differentiate to be minus 2 sine x. We are now going to substitute pi over 4 into this. Now obviously I can't substitute that into sec squared using my calculator, but I can substitute into cos. Sec squared is 1 over cos squared. So if I type in 1 over cos squared pi over 4, that's the same thing as me doing sec squared pi over 4. And then I can do 2 times sine pi over 4. And if I type that into my calculator, I'm going to get 2 minus root 2. So that's my answer for part I. Now moving to part II. Given that x equals tan 1/2 y, prove that dy by dx is 2 over 1 plus x squared. I'm going to need a bit of room for this, so let me come down to the bottom here and let me just copy this down. X equals tan 1/2 y. So let me differentiate this first of all to find dx by dy. Now I know that tan differentiates to be sec squared, so I'll get sec squared 1/2 y, and then by the chain rule I need to multiply by the derivative of the inside function. So the derivative of the half y is 1/2. So this is my dx by dy. I am now going to do the reciprocal of that to get dy by dx. Now, the way this is currently written at the moment, it might be quite awkward for you to be able to see what the reciprocal is going to be. So instead of writing it like that, I'm going to rewrite it like this, just so it's a bit clearer. Obviously, 1/2 sec y is exactly the same as me saying sec squared y over 2. So that the reciprocal of that then will be 2 over sec squared half y. Right, I've got the 2 on the top, so that matches up with what I'm trying to show. I just need to try and show now that sec squared 1/2 y is the same thing as 1 plus x squared. Well, I know that sec squared let me just talk generally for the moment. Sec squared theta is equal to tan squared theta plus 1. So therefore, sec squared 1/2 y is equal to tan squared 1/2 y plus 1. And the tan half y I know is just x. So I can replace this tan squared half y with x squared. So that completes my proof for part II. Let's move to III now. A bit more room. Given that y equals e to the minus x times sine 2x, show that dy by dx can be expressed in that form. Excuse me. Right, so I need to differentiate this. I notice that it is a product. We've got the e to the minus x, and we've got the sine 2x. So we're going to have to use the product rule to differentiate this. So let's start off by saying u equals minus x and v equals sine 2x. Differentiating then, so the exponential will differentiate to be the exponential, but I need to multiply by -1 because of the minus x on the inside there. Sine differentiates to be cos, but I need to multiply by 2 because of the 2x on the inside there. Now applying the product rule, which remember is u dash v plus v dash u. Excuse me. Right, u dash is minus e to the minus x times v, which is the sine 2x, plus v dash u is 2e to the minus x times cos 2x. So the u dash times v is that. The v dash times u is that. Right, so I've finished the differentiation and got this now. I now just need to try and rearrange that and make it look like this. So first thing I'm going to do, I notice I've got this exponential in both of these terms, so I'm going to factorise that out to leave me with a minus sine 2x plus 2 cos 2x. And the other thing I'm going to do here before I do any trigonometry is I'm just going to swap these two around so I have the positive at the front. Right, I need to rewrite this with this cos 2x plus alpha and an r. I can see I've got the exponential. This exponential here matches up with my exponential here, so that's good. But I need to turn all of this into my r cos 2x plus alpha. So let me expand that. Let me expand my r cos 2x plus alpha and then compare it. So first of all, expanding just the cos 2x plus alpha using the addition formulae in the formula booklet. I'll get cos 2x cos alpha minus sine 2x sine alpha. Now multiplying that through by the r. Right, let me compare that now with what I had in my differentiation. I've got a cos 2x here, I've got a cos 2x here, which means that my r cos alpha will have to equal 2. So let me write that down. R cos alpha has to equal 2. Similarly, I can see I've got a sine 2x here and I've got a sine 2x here, which means that my r sine alpha would have to equal, well, 1, because the coefficient of sine 2x there is 1. So my r sine alpha has to equal 1. In order to help me work out what r and alpha need to be, I can divide through, so I have my trigonometric ratios. And now just draw a quick little sketch of a right angle triangle where this angle is alpha. The cos alpha gives me the adjacent over the hypotenuse. The sine alpha tells me the opposite over the hypotenuse. So I can now work out r by using Pythagoras. R squared equals 1 squared plus 2 squared. So r is root 5. And I can work out the alpha by doing tan alpha is the opposite. Divide by the adjacent. So when I do tan inverse, I get 0.464. Excuse me. So what that means then is if r is root 5 and alpha is 0.464, I can replace these brackets with root 5 cos 2x plus 0.464. And this is now in the exact form that I needed to show it.